Hey, fellow space-time travelers! Ever wondered why time slows down when you're speeding in a spaceship? Or why your GPS knows you're lost before you do? Today, we're breaking down Einstein's mind-blowing theory of relativity. We'll explore how it warps time, twists space, and makes you the coolest science nerd in town. Ready to bend your brain like a pretzel? Let's dive in. Today, we're embarking on a mind-bending journey to unlock the secrets of Einstein's groundbreaking theory. Buckle up, because we're about to warp our way through the cosmos. First, let's set the stage. It's 1905, and a young patent clerk named Albert Einstein is about to turn the scientific world upside down. He publishes his special theory of relativity, challenging centuries of established physics. But what exactly is relativity? At its core, it's the idea that the laws of physics are the same for all non-accelerating observers. Sounds simple, right? Well, hold on to your hats, because the implications are anything but. Let's start with one of the theory's most famous aspects, the speed of light. Einstein proposed that the speed of light is constant for all observers, regardless of their motion. This might not seem revolutionary, but it leads to some pretty wild consequences. Imagine you're on a spaceship traveling at nearly the speed of light. You shine a flashlight forward. According to Einstein, the light from your flashlight is still traveling at the speed of light relative to you. But how can this be possible? Something's gotta give, and that something is our common sense notions of time and space. Enter time dilation. As objects approach the speed of light, time slows down for them relative to stationary observers. This isn't science fiction, it's been proven. Atomic clocks on fast-moving planes tick slower than those on the ground. GPS satellites have to account for this effect to maintain accuracy. But it gets weirder. The faster you go, the more mass you gain. If you could reach the speed of light, which you can't, you'd have infinite mass. This is why nothing with mass can travel at light speed. It would require infinite energy. Now let's take a giant leap to 1915. Einstein expands his theory with general relativity, incorporating gravity into the mix. He proposes that massive objects warp the fabric of space-time itself, creating what we experience as gravity. Picture a heavy bowling ball on a trampoline. The ball creates a dip, and smaller objects roll towards it. That's essentially how planets orbit stars, or how light bends around massive objects in space. This part of the theory led to some mind-blowing predictions. The bending of light by gravity confirmed during a solar eclipse in 1919 was one such prediction. The existence of black holes, regions where gravity is so intense that not even light can escape, was another remarkable forecast. Additionally, the theory predicted the existence of gravitational waves, ripples in space-time caused by massive cosmic events, which were first detected in 2015. These groundbreaking predictions have profoundly shaped our understanding of the universe and the fundamental forces that govern it. Einstein's theories have withstood over a century of scrutiny and testing. They've not only reshaped our understanding of the universe, but also enabled practical applications like GPS and more accurate space exploration. Einstein's legacy inspires us to keep pushing boundaries, questioning the unknown, and exploring the frontiers of knowledge. It's a reminder that curiosity fuels discovery, and that each new breakthrough builds upon the genius of those who came before. So next time you gaze at the night sky or ponder the mysteries of gravity, remember Einstein's gift to humanity, a deeper understanding of how our universe works. Keep exploring, keep wondering, and who knows, maybe you'll uncover the next cosmic revelation. Thanks for joining us, and until next time, let's continue our cosmic journey together, unraveling the wonders of the universe and celebrating the enduring legacy of Einstein's genius.